Okay, today we're going to see how do we use the state space form. I propose the same example that we have done in a past lecture to be able to obtain the state space form here. And in this case, we need to enter the bond graph model onto the CAMPG software and produce the state space form. We can do also the same example by hand and using the block diagram method, which we have seen in a past lecture, how we obtain the second order differential equations for the system, and then we converted it into 4 first order differential equations. So that's also a state space form. But right now we are going to produce the state space form and learn how to use it. So the steps that I have outlined on the right hand side, as you see, are to obtain the state space form either using block diagrams or bond graph methods, and use the ABCD matrices as a single simulink block. Those are the objectives that we have today. So what we'll do is, let me just have a little better view of the screen in here, and there's more space in here. So why don't we go and put this bond graph model into the CAMPG software, and we'll go and run CAMPG for a second. Okay, so let's run CAMPG here. Put this window perhaps a little bit to the right so I can have my bond graph that I want to draw on the left hand side. And I'm going to say do this a new file, and then I will enter this bond graph model. If you want to enter it with the same bond numbers, you just build them in that sequence, and so that's what we will do. So here we go and put the SF down here, and then I put the 1 over here, and then we do this, and then for number 2 we put this one in here like this, and then 3, which would be with the 1 to the right over here, building it in CAMG. You are just transferring from what you have on paper. So in here we have this 1 over here, and then this, that's number 5, whereas number 6 is over here like this. And then I, which would be on this side, number 7, and then we have number 8, which is this 0 over here, and then number 9, which would go over here, and then you have a 10, which is this C element right there, and then we have the R element over here, yeah, and then you have this one over here, and then you have the I element, which would be, well, we have the I element over here, but we need the SE is the next number, so we'll follow what the, and then finally this. See, I made a mistake, so I need to delete this because instead of writing an I just type a 1 in there. I just click the wrong icon, so I am fixing it now. Okay, This is if you want to correct the bone graft model to make it pretty, you could just move this using the move command, and then we could just do the same thing for another one in here, which would be from here to here. And we still need a couple of more to make it totally straight. See here. There we go. Let's see, single, we go from here to here. There's totally, perfectly well. You know, we have this always straight and nice and neat, same bone graft model with the same bone numbers. And so now we go to the MATLAB interface in here. Okay. So what happens in here is that CAMPG is going to produce these files that go in are ready for MATLAB. And the file we're going to concentrate on for today is the one that we need. We need to work it out. And that is, let me see if we don't have any windows in the back that are open. In fact, we don't. So there we go. Still coming up. Okay, so we produce the files in MATLAB. You see CAMPG produced CAMPG mod, CAMPG QU. Just to remind you, this is the file for initializing the parameters. This is the file for the equations of motion in individual form, the constitutive laws. This, however, is CAMPG SYM is the file that contains the equations in the Cauchy form, and it has the state space form. So you see there's one equation, there's two equations, there's three, and there's four. So right after you run this in just as CAMPG delivers this, you could actually run this and immediately you see what MATLAB does. Obtains, let me make it all bigger here. Okay, MATLAB has produced the state space form, the A and B matrices, but doesn't know anything about the C and the D matrices because we have not specified that. So that's why you get this just blank matrices basically. But in here, A and B are already done. So what we need to do is to go back to the files where you have this this form. So and tell in these files which variables we want as outputs. So let me just put that one away, and you can see in here if the output is the force on the damper, it is very obvious that that is the E11 variable, and the force on the bottom spring would be E sub 4. So we have E11 and E4 as outputs. So we go in here into this file, and then we go to find, find. First of all, we have E11, which would be the force on the damper. Yeah. If you search for it, you come to this place where on this file the output equation for E11 is specifically already derived. So all we do here is we activate this, and we call this is my output number 1 is E11. And then this question mark is saying which order in the C and the D matrices would be. So we put number 1, so they are the first rows of the C and the D. And the other one was E4. So we go in here and we say E4. And then again, that's the equation already derived automatically by the computer generated equation using CAMPG. We call this is our output number 2, and this is our output, let's say number 2, like that. Okay, so there we go. So in here, if you run this, let me make sure they see. If you run this, we need to see the MATLAB window to be able to see it. So let me bring it up. So if you run the file right here, let's close this one so we can see good. This is what happened. It says, look, you have 3 inputs in here, SF1, SE6, and SE13. Your state variable vector is in this order. And then this is the output vector is output 1 is E11 and output 2 is E4. Then you have the A matrix right there. You have the B matrix right here. Then you have now the C matrix. And you have also the D matrix. So we have produced them all in symbolic form. Now, if I want to do, let's say, the step and impulse response of the system here, using these matrices, what should I do? The first thing I gotta do is to produce the, we will have to give it some values, because as is, you know, the computer doesn't know what the values of C's and the I's and everything are. But if you want a system response, we're going to have to give it some values. Now, this file, CAMPG-SYM, is designed so that it does more than just a state space form. Let me show you what I mean. Perhaps we'll concentrate on the file itself. See, here's what it does. You have the ability here, it says, to generate the A, B, C, and D matrices, right? Then all these things are commented in here for the initial conditions. It says, you know, these are the physical parameters, basically. So you could potentially enter some numbers here and produce the matrices in numerical form, and then you can do calculations. It tells you what the inputs are, and it tells you what the state vector is. You know, when we write it semicolon here, it means the vector is vertical, right? That's the way we write. It has the equations, as I told you, but it has each of the rows is defined here, the A, B, and C. But this is for the output 2, which is the E4, and this is for the E11 down here. Okay. But think about this. It prints the matrices, but then it does, it is already designed to do a few things beyond the state producing just the matrices. First of all, it will produce give you the rank of the matrix, and it will actually produce the characteristic polynomial of the system. Now we need to talk a little bit more about this. And then it will produce the transfer functions, and it's designed to produce all the transfer functions, but at the end, at the very end, it has the to do the step and impulse response. So one possibility here that we have is we'll put some numbers in there and we'll do the step and impulse response. So how do we do this? You come up here and we are going to give some numbers to this. Let me see if we, hopefully I can get some reasonable numbers in here just to get this simulation going. This C4 is the bottom spring. Put this 1/40 here. This I7 is the bottom one. Let's put this to be a 2. Let's see, let's do a similar thing like 1/50 maybe. And then this R1, let's give this a 3 just for the sake of example. And then let's give this a 5, yeah? So having done this, I can go in here and just run it. But before I do that, I better have my MATLAB window visible so I know what it's doing. Okay, so this is, if I run it in here, okay, this is Control C. There we go. Let's go here, run. Okay, let me see. Did we miss? We might have missed a parameter in here. Well, let's do it again so that I know exactly what's doing. So we have a slight error in there, and we're going to go and see what it is. It says line 21. Okay. Okay, we run this file and then we just restarted MATLAB. That's all I did. But you can see here now the matrices now are numeric matrices. They are numeric matrices, the A, B, and C, and the D matrices. And then it gives me as order 4, gives the characteristic polynomial of this. We'll talk about the transfer functions a little later, because let's just not dwell too much into that. But what I'm interested is in the impulse and step response of the system, and this is what the computer will do. It does does these body plots, but for now I want to concentrate on just on the impulse and step response, which is what we have right here. See, it has 2 outputs and it has 3 inputs. The computer produces the impulse and step response for all relations between the output and the input. So you produce it all like that. Okay, but this is what I was trying to say to you is this. In here, if you already have the matrices in here. You have, like, for example, A is this. You have B is this. You have C is this, and D is this.